Let's talk about the electric field of a continuous distribution of charges. Here I have a one-dimensional rod indicated in red, and I've placed it along the x-axis in a symmetric fashion with the left end at negative L over 2 and the right end at positive L over 2. So the rod's total length is L. Later on I'll take the limit that L goes to infinity in both directions. How would you solve a problem like this? Because it's a continuous distribution of charges, we cannot use Coulomb's law directly. We have to adapt it using elements. I'm going to assume that the distribution I have is the same on the left and the right, so there's a certain amount of symmetry in this problem. If that is not true, you cannot use this technique and you have to just do each side separately and then add them up vectorially. But the symmetry argument can be used whenever you have the left side and the right side distribution being the same. Assuming they are positive charges, the right element puts out an electric field which I'll call d sub E, and I'll call the charge element here dq. I'll call the mirror element dq prime on the left side, and the corresponding field it will put out will be called dE prime. If you look at the two vectors, you notice that the x components will cancel out, leaving only the z components to add up. Let's define this angle theta. That angle will also be theta here. So from that we can see that the components that add up are the sine components. So let's write down the magnitude of the resultant electric field at point P. It will be 2 dE sine theta, and I can even draw it. There it is. Let's try to expand these quantities. dE by Coulomb's law for the point charge is k times dq over r squared, where r is this distance from the charge element to the point in question. It used to be kq over r squared for a point charge, but now the point charge has been replaced by a charge element dq. Sine theta, let's call this distance z. Sine theta is simply z over r. Now, the biggest challenge is to write dq in terms of the distance dx. The variable that we have along the x direction is x, and this distance is dx. To perform calculus, we will need to find a connection between dq and dx. That connection is got by defining what's called a linear charge density. The linear charge density is denoted by the symbol lambda, and in this problem, lambda can be a function of x in general. It's defined as the rate of change of charge per distance, or dq by dx. If lambda is a function of x, I will demand that lambda changes the same way on the right side as it does on the left side, so we still have the symmetry argument. The simplest case, though, is for lambda not to be a function of x, and that's the simplest case I'll deal with. But I want to emphasize that there is nothing wrong with emphasizing lambda as a function of x, except that the integral might be too difficult to do by hand, and you may have to use a computer or Wolfram alpha. So the simplest case is a constant lambda case. Charge density, incidentally, has got units of coulombs per meter. So the simplest case would be the same number of coulombs per meter throughout the rod, meaning it's a uniform rod. Under these conditions, dq by dx is lambda naught, so dq is simply lambda naught times dx. Let's write down our expression. It's going to be 2k lambda naught, I'll put the z first, times dx divided by r cubed. Now r, by the Pythagorean theorem, is the r squared is x squared plus z squared. So that's going to be x squared plus z squared to the power 3/2. The total electric field E sub p is given by integrating. Now, because we have considered the mirror's elements, we're only going to integrate across half the rod. So it's from 0 to L over 2 of this quantity here. So that's 2k lambda naught z dx divided by x squared plus z squared to the power 3/2. This is not a difficult integral to exactly solve. So 2k lambda naught and z are all constants. K is the Coulomb constant, lambda naught I've assumed to be constant, and z is just the distance from the rod, which is also fixed. Let me just forget all that and worry only about the denominator then. I'm going to call this integral I. The integral I is the integral of dx divided by x squared plus z squared to the power 3/2. The proper technique is known as trigonometric substitution, which you have learned in calculus. And we're going to try the substitution x equal to z tangent of beta. For the moment, don't worry about what beta is. Later on, I'll show you what it actually means in terms of our original figure. Then dx is z secant squared beta d beta. Let's also see what happens to the denominator under this substitution. So x squared plus z squared will be z squared tan squared beta plus z squared, which can be written as z squared times tan squared beta plus 1. And tan squared beta plus 1 is secant squared beta. Finally, our integral becomes I equals the integral of, for dx, I'm going to substitute z secant squared beta d beta. And the denominator is raised to the power 3/2. So that's going to be z squared secant squared beta, the whole thing to the power 3/2. Now, because of this square and the half power, I will lose those powers, and I end up getting z secant squared beta d beta divided by z cubed secant cubed beta. One factor of z disappears. The secant squared and the secant cubed cancel out, giving me just secant in the denominator. Well, secant in the denominator is the same as cosine in the numerator. You observe that I've taken the z outside because it's a constant. The integral of cosine is just sine. Now, if you wish, you can rewrite sine in terms of the original variables. So let me do that here for a moment. If tan beta is x over z, tan is opposite over adjacent, so it's going to be x over z. Now, for those who are very curious as to what beta is in our original figure, tan beta is x over z, so beta must be this. In other words, beta and theta are related by being complements of each other. Beta is 90 minus theta. But that's just not important. Once you have that, you can write sine beta in terms of our original variables, and that's going to be x divided by this distance r. So that's x over z squared times the square root of x squared plus z squared. And we can write the final answer. E sub p is the integral from 0 to L over 2 of 2k lambda naught z dx over x squared plus z squared to the power 3/2. I've just copied down that expression there. That will be equal to, now remember 2k lambda naught z are still there, so it's 2k lambda naught z times this integral which I called I before, which is that, and between the limits of 0 and L over 2. One of the factors of z cancels out, and you can find out what this is. It's not particularly enlightening. Let me do it here. The 2 will cancel out with the halves, so I get k lambda naught L over z square root of z squared plus L squared over 4. Now what we're going to do next is ask what happens when L becomes really large. So limit when L goes to infinity. This can be done two ways. You can either go back to the original integral and solve it for the infinite length limit. If L goes to infinity, then beta must go to pi over 2, and the answer will simply be 1 over z squared when you evaluate it. So that would be one easy way of doing it. The other way you can do that is, if L goes to infinity, you can neglect z squared compared to L squared over 4, and then you'll end up with the same result, basically. If you neglect this, if you neglect z, you're going to get L over 2 So let me just do this. Let me just do this. So let's take the limit EP as L goes to infinity. So here I'm going to get, remember that's going to be neglected. So it's going to be k lambda naught L over C times L over 2. The L's will cancel out, and so I'll get 2k lambda naught over Z. And that is a very important result because it tells us that the electric field of an infinite line charge falls as 1 over Z, not as 1 over Z squared. 1 over Z squared is how the electric field of a point charge falls off with distance. Let's try to make sense of that. For this, let me draw the line charge vertically. Let's suppose I'm some distance away from the line charge, and I'm looking at this line charge. Let me say I'm looking at it using a 30-degree angle. So that's a 30-degree angle, and I'm looking at it. I see only a small portion of the line charge, and that portion will give me my electric field. If I go far away from it, I'm going to see a bigger portion of the line charge. So definitely it's not going to fall off as quickly as it would if it were a point charge, because I'm seeing more of the line charge. But the fact of the matter is that I'm still far from it, so I'm going to lose some of the effect of each particular line charge element from being far away from it. So that's the reason why you have 1 over Z instead of 1 over Z squared.